You're watching TelecomTV. I'm Guy Daniels, Director of Content, and in a moment I'm going to be speaking with Qualcomm about the practical opportunities for mmWave 5G in Europe. What is the state of mmWave worldwide, and what work is involved with bringing the technology to fruition? How is the Qualcomm Engineering Services Group helping carriers deploy, test and tune mmWave, and where are we starting to see deployments? Well, joining me now to explain more are George Tsirtsis, Senior Director Technology at Qualcomm Technologies International, and Nicholas Waegner, who is Senior Director Program Management at Qualcomm CDMA Technologies. Welcome to both of you. Good to see you.
Good afternoon.
George, let's start off with a background to mmWave 5G and how Qualcomm is contributing.
Thank you, Guy. So Qualcomm has been in the forefront of communications technologies for over 30 years. And now we are happy to be again at the forefront of 5G technology. mmWave is an integral and important part of 5G. So before we go into more details, I want to say a few words about what makes mmWave so special. You all probably have seen the gigabit speeds that are available on mmWave. We have, in fact, been demoing this kind of thing for a few years, starting from labs and then in big conferences like in MWC. But since last year, we have seen the same impressive gigabit speeds in commercial networks using commercial devices. And this is, of course, very, very important as it validates the technology. Behind these peak speeds, however, what is hidden is a very large amount of capacity and low speeds. And these are the aspects that we think will make mmWave particularly impactful in the long run. So mmWave will provide high speeds to many users at the same time with low latency. So let's look now at where are we with 5G deployments in the world. In fact, 5G has been commercial now available in all continents. As you see here, we have 5G deployments in many countries. And a lot of them, of course, are sub-6, but many are mmWave. mmWave started in North America last year and now is expanding in Asia with deployments in South Korea, Japan, other Southeast Asian countries, as well as Australia, but is also coming to Europe. In this map, you see the countries that currently have mmWave spectrum available for commercial use. And we expect that a lot more countries will get that in the next year or so. So in fact, we think 10 more countries will be added to this map in terms of auctions or otherwise allocated mmWave spectrum in 2021. In parallel, though, we get now the first commercial mmWave service from Fastweb in Italy. This is fixed wireless access with mmWave. And also, we see Motorola Edge Plus be the first smartphone device that is coming with mmWave in the region. It's going on sale in Russia, and we expect mmWave services there to become available in the next few months. In parallel, many other operators across different countries are trialing and piloting the technology for launches in the next months and years. European operators are going to be able to leverage an already quite healthy ecosystem of end devices that is available for the global markets. Everything you see on this slide supports mmWave. Smartphones, you see laptops and modules, as well as CPEs and mobile hotspots. And all of these devices are leveraging Qualcomm technology, from our Qualcomm Snapdragon application processors to 5G modems and RF subsystems. This is our latest commercial offering. This is the Snapdragon SDX60 with RF subsystem. It is a very comprehensive package. It supports all the cellular generations from 2G, 3G, 4G, as well as sub-6 and mmWave 5G. And also, we provide not only the baseband part, but everything from baseband all the way to the antenna in terms of RF subsystems. And in the case of millimeter wave, we have developed fully integrated antenna module systems. We are now on our third generation of millimeter wave antenna modules. QTM 535 that you see here is our latest offering. This will be incorporated in devices that are coming next year to the market. And it has the thinnest profile we have developed so far. But even QTM 525, its predecessor, which is incorporated in the devices that you saw in the earlier slide, is very, very thin and was designed to go in a smartphone form factor from the beginning. So Motorola Edge Plus, for example, and other devices like it are very thin and very much a normal smartphone form factor. We are also developing specific millimeter wave antenna modules for fixed wireless access application. And what you see here is a reference design that we provide to our device partners, OEMs, who develop, of course, their own designs. But these CPE-specific solutions are able to transmit in much higher power than the regular smartphone modules. And you will see later in the presentation by Nicholas some very impressive results about the kind of range that can be achieved with these millimeter wave modules. Also, one thing to note is that our smartphone solutions are able to operate in all the global bands. So OEMs can create global SKUs and can bring devices developed from one region to another as needed. So we support all of the 26, 28, and 39 gigahertz bands. So these are the main products we have for millimeter wave end devices. We also produce technology for like FSM chipset for small cells, which I didn't go through today. But the technology portfolio already enables many use cases. And we think millimeter wave will have an impact in both consumer side, which where it will change the way we consume content, we do gaming, the way we participate in live events, as well as in enterprise and industrial applications. So Nicholas now will go over some specific deployment scenarios and the performance we see millimeter wave being able to achieve based on both simulations as well as, importantly, field and commercial networks. Over to you, Nicholas.
Thank you, George. My name is Nicholas Waegner, and I work for an organization called Qualcomm Engineering Services Group. We work worldwide with operators to assist them in evaluation, deployment, and optimization of new technologies, new wireless technologies. And in the next section, I'd like to share with you some of the insights and case studies that we have from our work on millimeter wave, where we've already been engaged for several years already. As George presented, 5G millimeter wave offers great new opportunities, not least because of the bandwidths available in the spectrum. In Europe, we're talking about 3 gigahertz of spectrum in the pilot 26 gigahertz band. And this, for instance, in outdoor deployments, would significantly enhance a smartphone user experience, particularly in hotspot areas in inner cities. And then moving indoors, 5G millimeter wave could be a complement to existing cellular deployments, indoor cellular deployments, or Wi-Fi, bringing that capacity to bear to offer superior speeds and enabling new applications. Looking first at that urban deployment, and one of the questions that was posed to us was, what is the impact of deploying millimeter wave in cities? To answer that, we took simply the existing 4G sites within various cities in North America, in Asia, and in Europe. And so what would happen if we deploy millimeter wave at those same sites? The remarkable result was that the outdoor coverage achievable just by reusing those sites could be up to 75%. And given the bandwidths available of 800 megahertz, for instance, this would translate into a median burst rate of over 2 gigabits per second, up to 2.7 gigabits per second in certain scenarios. Of course, it's not always feasible to cover an entire city center with this technology. We might focus on hotspot areas, depending on the density of existing sites, but there are techniques available also in the standards evolution to further enable this, and we'll touch on that towards the end of this presentation. Now, those were simulations, but these networks are already deployed, as we mentioned previously, so there's an opportunity to go out into the field and actually measure them. And here are two examples from cities where we've been in the field and we've measured actual performance using commercial devices. The first example, the one at the top, is an example of a site covering the forecourt of a shopping mall and the parking area. And we took measurements at different distances from the site. At a distance of 30 meters, so near cell, we could measure 1.8 gigabits per second of throughput. And even at the far cell location, almost 300 meters from the cell site, we still could sustain 1.3 gigabits per second of throughput. Contrast that to the speeds available in 4G at the same locations, which are an order of magnitude smaller, showing the benefits of deploying 5G to the user in such a scenario. And these results are borne out in additional measurements that we took. There are examples in the two examples at the bottom of this page from another city, showing measurements also taken close to the cell site or a distance up to 400 meters. And there we also saw throughputs of 1.7 or more gigabits per second achievable. So demonstrating that we can significantly enhance mobile broadband experience in urban areas using millimeter wave. Millimeter wave now is finding application in other areas, moving indoor or to the home. And in the next slides, I'd like to cover some of these scenarios of enterprise and industry applications, venues such as stadia, transport hubs, where we also have a high capacity requirements and high footfall, and in fixed wireless access in providing broadband access to the home. So we see millimeter wave in the enterprise environment complementing existing cellular deployments, indoor cellular deployments, or Wi-Fi. Indeed, we could conceivably reuse some of the infrastructure already deployed there on the sites, the cabling, the power supplies, to overlay millimeter wave. And so as a study, we took an existing office floor, this is around 2,500 square meters, and performed some measurements in this environment just to calibrate our models to make sure that the models are tuned and our simulations would match what we would see in the field. And took the existing Wi-Fi access points, the locations of these Wi-Fi points, 20 of them in this scenario, as locations for the millimeter wave antennas. You can see they're deployed on ceilings, in conference rooms, in corridors, in reception areas. So simply overlaying millimeter wave or adding millimeter wave to these locations, we could see that we could cover the entire floor, provide coverage to the entire floor with millimeter wave using these sites. And what's more, with bandwidths of 800 megahertz, we're able to offer user experience of 5 gigabits per second peak in this environment. Therefore, enabling some of the applications we've mentioned, connected 5G and millimeter wave connected laptops, remote cooperation, AR, VR, all possible using 5G millimeter wave. Another enterprise environment might be in industry, and here's a typical shop floor with machines and metallic surfaces. And we performed a similar study of such a shop floor. This is around 500 square meters. Also calibrated our the model, the propagation model, so that our simulation closely resembles what we measure in the field. And you can see it's a complex environment with line of sight, non-line of sight, the reflections of the different surfaces. Nevertheless, with three antennas deployed for millimeter wave in this area, we could achieve 100% coverage. And what's more, offer peak throughputs also, assuming 800 megahertz, of 4.2 gigabits per second. And this, of course, will enable a whole host of industrial applications in this type of environment. So those are simulations, but we do have deployments indoor as well, and this is one example, and we went out and measured it. So here you see a millimeter wave antenna deployed on the balcony of a first floor in this building. The antenna is illuminating the atrium waiting area of the building, and our simulation studies, our coverage studies show that we get good coverage of the area in front of the antenna. But when we take a device, in this case a commercial device again, and took measurements in this area, we also saw coverage in non-line of sight environments, such as around the corner into the auditorium that you can see on the bottom left, or even on the ground floor below the antenna, behind the antenna, we also get coverage, which underlines one of the key aspects, that reflections are a friend in millimeter wave systems. So even in non-line of sight scenarios, we can see, as you can see in the bottom left, a snapshot of the screen of the device, throughputs of over a gigabits per second achieved in non-line of sight scenarios. Turning now to venue type deployments, stadia type deployments, and this is I would say a sweet spot for millimeter wave deployments, where millimeter wave antennas with a very defined footprint, the opportunity to create good isolation between neighboring cells, allows us to create excellent coverage and excellent signal quality in a very dense environment. And furthermore, of course, we don't have to contend with in-building penetration losses or other types of losses, and the distances are relatively short between the subscriber and the spectator and where the antenna is located, typically, say, on the roof level of such a stadium. So we have already generated designs for millimeter wave deployments in multiple stadia. And here's one example of a very large stadium with 100,000 seat capacity. And we can show that merely 15 antenna sectors are required to provide coverage. And what's more, if we assume a 400 megahertz bandwidth, we can also provide excellent user experience, excellent throughputs to the spectators on a medium basis of 700 megabits per second or more, or even at cell edge of 100 megabits per second are possible. Those are simulation, but these systems are already being deployed and continue to be deployed. And here's an example of measurements that we took in another stadium. This time the bowl is covered with 8 antenna sectors, well nigh 100% coverage with those. The same bowl area is covered with 121 4G sectors to provide coverage and capacity. And measurements that we took during the event in the stadium showed that 5G millimeter wave subscribers, or we could benefit from a tenfold increase in the throughput at the same locations relative to 4G users. This can, of course, be used to enhance the existing applications that users might use on their devices, but also the creation of new applications that a stadium owner or a sports team might like to offer to or an operator to their subscribers. A similar area of high footfall, high capacity demands exist in transportation hubs, railway stations, subway stations, airports, where there are end users, but there might also be professional users having specific requirements. Or there's an opportunity to create, again, new experiences for visitors at these environments. And we've performed a number of designs for such locations. Here's an example of an airport terminal, an airport concourse. It's quite a large surface area of around 15,000 square meters. And you've got the waiting areas around the gates, you've got a business lounge, you've got shops, you've got a food court. And with relatively few millimeter wave, sites were able to provide 100% coverage and also throughputs of in excess of 4 gigabits per second. In a similar environment, so actually in another transport hub, this case a railway station, we actually recently had the opportunity to test a real system and to gather actual measurements. And here are some of the results that we have from this. So it's also a system with 800 megahertz of bandwidth. That is then 8 component carriers, each of 100 megahertz. And as you can see on the downlink, we could achieve throughput rates of 3.6 gigabits per second. You can see the signal changing. There are objects, there are people moving around, so it's a real environment, but nevertheless, these throughputs are sustained. And also in the uplink, in this case, we actually had carrier aggregation in the uplink, so 2 100 megahertz carriers for a total of 200 megahertz. And this enabled us to measure 271 megabits per second in the uplink also. Another key enabler for some of these additional applications or user experiences that we would like to offer subscribers or professional users in such environments. And finally, I'd like to turn to millimeter wave as a solution for fixed wireless access. For instance, in urban areas, to provide a fiber over the air type solution, to provide connectivity to entire buildings, or in suburban or rural scenarios, provide connectivity directly to the home. So we performed a study, a planning study for an urban environment. You can see the type of clutter of tall buildings. On average, these are around eight stories. And this translates into a building number of 2,500 buildings in a 2 square kilometer area. We'd estimate around 15,000 households would be in this area. And our simulations show that by using millimeter wave, as I said, to provide connectivity to the building and then distributing that connectivity through the building through some other means, we could offer to each of these households on average 159 megabits per second throughput, and in some cases, in best cases, throughputs of up to well nigh 2 gigabits per second would be possible. As we mentioned, we could also provide connectivity directly to individual households. For instance, in a suburban environment, and this is an example of a typical suburban environment in Europe, low-rise buildings, a low concentration of buildings, lots of greenery, lots of vegetation. And locating a cell site in this environment with 400 megahertz of bandwidth, we could show that at distances up to 600 meters from the cell site, we could offer to individual users 3 gigabits per second of throughput or more to these customer premise equipment, or even at distances up to 1.8 kilometers from the site, we'd still see throughputs of 100 megabits per second or more. These distances depend on the morphology, of course, but I would like to share some results of field measurements that we recently made with US Cellular and Ericsson in North America. We're using the extended range CPE that George mentioned earlier. We could measure actually throughput rates of in excess of 200 megabits per second at distances of 5 kilometers from the site, therefore enabling that broadband experience in such rural environments. And finally, I'd like to return to the point on urban deployments that we mentioned earlier. In some cases, it might not always be possible for practical reasons or economic reasons to provide backhaul to individual sites and therefore densify a network. But in release 16, the concept of integrated access and backhaul has been introduced, where we can also use millimeter wave and the extensive bandwidth available to us not only to provide access, but also to provide backhaul, in-band or out-of-band, to enable improvement of the signal coverage, and also the end user, improve the end user experience. And this is a simulation study that we performed, taking such an inner city environment with millimeter wave sites deployed, and then densifying it with these integrated access and backhaul nodes to extend the coverage. And we could see that we can significantly enhance the signal in this area, and this translates into a median improvement of the downlink rates by a factor of 2 in such an environment. So this and other evolutions will further assist us in the deployment and the offering of 5G millimeter wave services to subscribers in future. So thank you very much, and back to you, Guy.
Thank you very much, Nicholas, and also to you, George. Great insights into millimeter wave 5G and Qualcomm's activities. There's a couple of questions I'd love to ask both of you. George, you mentioned several millimeter wave initiatives in Europe that Qualcomm is engaged in, but really, what's been the response so far from the telecoms operators themselves? How keen are they on millimeter wave 5G?
Yeah, thank you, Guy. So in Europe, as you know, and as you saw in the global map I showed earlier, there has been a lot of sub-6 5G deployments. And this is because spectrum became available in Europe really across the continent over the last year in N78 3.5 gigahertz. And operators understandably have been focusing on that, as well as providing 5G in FTD bands. So a lot of the concentration of investment and attention has been on that side. Millimeter wave spectrum is becoming available more gradually. You saw there is only a few countries currently that even have access to the spectrum for commercial use. And there, the operators have been working on the background, as well as in other countries where operators have been trialing the technology and working with regulators for the spectrum release. So there is a lot of interest. We are very encouraged by the commercialization of millimeter wave already in Italy by Fastweb and in Russia also. And I think you will see over the next few months a lot more activities becoming public in this space.
Well, that's very good to hear. Do you think we're still in the early stages of seeing exactly what millimeter wave can offer? Are there still more benefits and scenarios and use cases that we have yet to really explore and discover?
Yes, for sure, the millimeter wave benefits will become more apparent over time. But we are already benefiting from commercial use of it in the US over the past year. And it's becoming increasingly apparent that there are many use cases where millimeter wave is clearly beneficial. Fixed wireless access is one of the more straightforward ones, but in EMBB, so traditional cellular services, as well as importantly in enterprise and industrial, there is a realization of the benefits there. And these are areas where it takes a little bit longer for technologies to be absorbed, but there is definitely an increasing understanding of the benefits of the technology.
Thank you, George. And Nicholas, can I ask you, you had a lot of information in the presentation, some great information in there. One of the things that really struck me was the importance of co-siting. There seems to be significant advantages, especially with the higher frequencies.
Yes, Guy, I would say that co-siting, as we showed in our simulations, is an opportunity. So we demonstrated that exploiting co-siting, you can actually also achieve good coverage, outdoor coverage, using that, or co-siting within in the indoor environment to exploit existing infrastructure, passive infrastructure. So indeed, that is a benefit. And of course, we can then take a more specific view of millimeter wave to further enhance that coverage through some slight modification to the cell sites or addition of sites. But as a baseline, it is true that we can already make great use of existing infrastructure.
And there's a lot of focus at the moment generally on improving home broadband. You've given us details on how millimeter wave 5G can help in this scenario, but is it yet a viable alternative to existing solutions?
I would say that's indeed the case. I mean, here we're able to exploit the extreme bandwidth that we have in this spectrum, 400, 800 megahertz of bandwidth available to deliver these services, and so that is a considerable aspect of capacity, but also enhances the single user experience in this environment. So yes, it is a viable option and is actually being exploited now. As George said, millimeter wave will be used for delivery of FWA services in Europe already.
Great. Well, Nicholas and George, thank you both very much for joining us and talking us through your presentation. I've got a lot more questions, but I think our audience do as well. If you have any questions at all of your own about millimeter wave 5G and the role Qualcomm is playing in its development and commercialization, then please stay with us and join us on our live Q&A program, which will be starting very shortly. George and Nicholas will both be back to answer your questions, and we shall be going live with the Q&A at 2 p.m. UK time. That's 3 p.m. CET, so very, very soon. So until then, thank you for watching. Please join us for the live Q&A, but for now, goodbye.